In this lesson, we're going to talk about functions expressed in the form y equals af k times x minus d plus c. Okay? We're going to talk about each of these positions, the effect of the values of a, k, d, and c. Well, position number one is the value of a. What happens with whatever number occupies this position right here is that we get a vertical stretch if the magnitude of that number is greater than 1. So for instance, if the magnitude of a, if the value of a is -2 or the value of a is 3, in other words anything with an absolute value greater than 1, we're going to have a vertical stretch. On the other hand, we'll have a vertical compression if that value of a if the magnitude of a is less than 1. So for example, if a was -1/4 or a was 1/2, we would get a vertical compression. If the value of a is negative, then we're going to get a reflection in the x-axis. Now, all of this can be accommodated algebraically by multiplying the y-coordinate by a. Okay, so when we come to graphing these functions, we're going to ultimately multiply the y-coordinate by a. Now we can talk about the value in the second position. That's what we call k. Now k is in the argument of the function or the input of the function, and it's multiplicative. What happens is if the magnitude of that number is greater than 1, so for instance if the number is -3 or if the k value is 4, we're going to have a horizontal compression. Now that might be counterintuitive, but the larger this magnitude is, the more compressed horizontally our graph will become. On the other hand, if we have a small magnitude, in other words a magnitude less than 1, so we could have a k value of -1/2 or a k value of 2/3, anything with an absolute value less than 1, then we're going to have a horizontal stretch. And if the k value is negative, we're going to have a reflection of the original function in the y-axis. Now algebraically, all of that can be accommodated by dividing the x-coordinate by k. Our next value to talk about is the value of d. Well, we're going to translate right if d is positive. So for instance, if I see a minus sign in the actual equation of what I'm trying to graph, for instance if I saw x minus 4 in this portion of my simplified expression, then what I would do is move 4 units to the right. So translate right if the d value is positive, which means if I see a negative sign there. On the other hand, I'll translate left if the d value is negative. So if I saw x plus 4 here, I would translate 4 units to the left. Okay, and so in other words, if I saw a plus sign, I'd translate 4 units to the left. That's very similar to what we did with parabolas. If you recall, when we dealt with parabolas in vertex form, if we had x minus a number and the quantity was squared, our vertex had a positive x value. But if we had x plus a number and the quantity was squared, we moved to the left instead. Well, the same thing's happening. We're going counterintuitive here. So ultimately, all of that can be accommodated by adding d to the x-coordinate. And our final value is c, and what that means is we're going to translate up if c is positive and translate down if c is negative. So what we're going to do is we're going to add c to the y-coordinate. Now if you notice all these algebraic statements we made in red at the bottom, multiply the y-coordinate by a, divide the x-coordinate by k, add d to the x-coordinate, and add c to the y-coordinate, we can put all of those together on one page and maybe switch the order up a little bit. And what we've got is that we're going to need to divide the x-coordinate by k and also add d to the x-coordinate. So in other words, we're going to take the original coordinate and transform it to x over k plus d. X divided by k, add d. Similarly, we're going to multiply the y-coordinate by a, and we're going to add c to the y-coordinate. So what that means is we're going to take the value of y, the coordinate of y, and we're going to transform it to become ay plus c. And so x is transforming to this new value, and y is transforming to this new value. And the effect of both of those comments together gives us this mapping formula. If xy is a point on the parent function, then it's going to be now mapped onto x over k plus d and ay plus c. Okay? This is a very important formula for our transformation purposes. Now, we've dealt with, in a previous lesson, 4 parent functions. One of them is y equals the square root of x. Well, if y is the square root of x, then is our parent function, then what we want to do is get our function in the form y equals a square root of k x minus d plus c. So this would be like af of kx minus d plus c. We want to arrange it to look like this. If our parent function is 1 over x, then we want to make our function that we're trying to graph y equals a over k bracket x minus d plus c. Okay? The argument is in the denominator, so we put the argument in the denominator, we multiply by a, and we add c. Next, if we have y equals the absolute value of x, well, when we go to graph a transformed function of that, we're going to hope that we can arrange it so that we have y equals a times the absolute value of k, x minus d, plus c. Okay? It's like a f of kx minus d plus c. And finally, if we have x cubed as our parent function, then what we're going to do is try to make our function that we're trying to graph conform to this. Y equals a, and then in brackets k bracket x minus d, and that entire amount cubed plus c. So this is the function, this is the argument of the function, and we're multiplying it by a and adding c. Okay? So this is also going to be important to remember, to try to remember what our friendly form of a transformation request looks like. And we're probably going to have to do some algebraic manipulations to the question to force it to conform with what we like it to look like. Now, you might be wondering, are there default settings for a, k, d, and c? Well, a is something that we multiply and k is something that we divide, so those identities are both 1. D and C are both quantities that we add, and so their default settings are 0. And so the default setting for A and K are 1, D and C are 0. And then you might say, well, does it matter what order we do the transformations? And basically, it goes like this. The y-coordinate is multiplied by A and then C is added. Well, BEDMAS would tell us to do the multiplication portion first and the adding portion second. So make sure that we deal with the A before we deal with the C. And similarly, BEDMAS again would tell us that when we're dealing with the x-coordinate, we should make sure we divide by k before we add d. So we should deal with any horizontal reflections or compressions or stretches before we deal with any horizontal translations. And same with this, we should deal with any vertical stretches or compressions or reflections before we deal with any vertical transformations. Okay. All right, well, let's try our first word problem together here. We're going to try and describe the transformations that apply to the graph of y equals root x to obtain the graph of y equals 3 square root of negative a half bracket x minus 2 plus 1. And then we're going to graph that function and state the domain and range. Well, starting first with the verbal transformations. When we have it written in this form, we see that this is our a value, our k value, our d value, and our c value. Well, a equals 3, according to our information in the earlier page, means that we have a vertical stretch by a factor of 3. Okay, The magnitude is greater than 1, so we have a vertical stretch by a factor of 3 because we're going to multiply y by 3. Well, k equals negative a half. Well, that negative sign means we have a reflection in the y-axis. When k is negative, that's the case. And the 1/2, since we're dividing our x-coordinate by a half, that's like multiplying it by 2. So we get a horizontal stretch by a factor of 2. Our d value is 2, that means we have a translation 2 units right. And our c value is 1, so we have a translation 1 unit up. Okay? So those are the verbal statements of transformations. Let's see if we can find some points and graph it. Well, when we have this equation given to us, like we said on a previous page, a is 3, k is negative a half, d is 2, and c is 1. And we try to remember this mapping formula, and that was given to us earlier on one of our earlier pages. Okay, and it's really important that we remember that mapping formula. Okay, so I write it right here. And now we have to remember some of the points on our parent function. Well, our parent function is y equals square root of x, and that parent function contained the points 0, 0, 1, 1, and 4, 2. Well, if xy is now 0, 0, and here are a, k, d, and c values, then we can put that xy through this mapping formula. 0, 0 will map onto 0 over negative a half plus 2, comma, 3 times 0 plus 1. Well, that's like 0 plus 2, comma, 0 plus 1, which is 2, 1. So the point 0, 0 is going to map onto the point 2, 1. The point 1, 1 is going to map onto 1 over k plus d times 3 times 1 plus c. And evaluating this using BEDMAS gives us an x-coordinate of 0 and a y-coordinate of 4. So the point 1, 1 maps onto the point 0, 4. And finally, the point 4, 2 will map onto 4 over k plus d and 3 times 2 plus 1. And that simplifies to negative 6, comma, 7. So we've got the points 2, 1, 0, 4, and negative 6, 7. So we plot them, 2, 1, 0, 4, and negative 6, 7. Now, it's good to have a recollection of what the parent function looks like. The parent function y equals root x looks like this. But now the point 0, 0 has moved here. And the point 1, 1 has moved here. So we have to try to treat it the same way. Now, the point 4, 2 has moved out here, and our job is to go through the point 4, 2 and continue on infinitely. Okay? So I'm treating these points here the same way I originally treated these points here. And this is the curve that we were asked to sketch, the one in blue. The one in black is irrelevant, we just used it as a guide. And if we want to state the domain and range, we can say that the domain is x such that x is less than or equal to 2, and x is an element of the reals. And the range is y such that y is greater than or equal to 1, and y is an element of the reals.